Hello and welcome back. Let us try to understand a little more about vector algebra. Now we are going to understand what is vector multiplication, what is commutative behavior of vectors, and then how to calculate length of a vector, what is a unit vector, and how to find projection of one vector on another. So let us start with commutative behavior of vectors or vector multiplication. If you take v1 and v2, if you have to multiply these two vectors, you need to transpose 1 and multiply, because the dimensionality of v1 is 4 by 1 and v2 is also 4 by 1. When you have to multiply two matrices, the number of columns should match number of rows of the first matrix. Number of columns should match number of rows of the second matrix, right? So to get that behavior, we need to transpose the first matrix. So then what happens? It becomes 1 by 4, 1 row and 4 columns, and this is 4 by 1. When you multiply these two, you get one number. Vector multiplication always gives you one scalar. When you multiply two vectors, you get one scalar. See this here? When I multiplied these two vectors, I transposed and multiplied 1 into 0, 2 into 1, and 1 into 1 and 4 into 1, and summed up all the 4, and I got 7. The same way, v2 transpose v1, right? Commutative means A into B is equal to B into A. It is commutative behavior, right? The vector multiplication is commutative. So v2 transpose v1 is also giving you 7. So this is equal. So vector multiplication is commutative. Okay, that we need to remember. And the next concept is how to find length of a vector. When I say a data point a vector, it is always represented as a column, right? You can actually have this data point like this here, v1 somewhere on x-axis and v2 on y-axis, and you can say that as a data point. But when we say vector, right, it will have a length and a direction. So to calculate this length, we can use Pythagoras theorem. This is v1, this length is v1, this height is v2, and square root of v1 square plus v2 square is the length of the vector. That is called as norm, L2 norm of a vector. We have used L2 norm in regularization, right? Ridge regularization uses L2 norm in linear regression and logistic regression. I hope you remember that. And to calculate length of a vector or L2 norm of a vector, you can use square root of v1 square plus v2 square. If the vector has got n number of values, then the length of the vector is square root of v1 square plus v2 square plus v3 square plus and so on vn square. So that is the length of the vector. And next concept we are going to understand is unit vector. When a vector's length is 1, then you call it as unit vector. If you take a identity matrix and take the first, any row vector or column vector there and try to calculate the length of it, you will get 1. Square root of 1 square plus 0 square plus 0 square is square root of 1 square is 1, right? So that is unit vector. But normal numbered vectors also, we can convert them into unit vectors. It is called as a normalization of vector. To normalize a vector and make the vector a unit vector, you need to divide each value with the length of its vector, length of the vector. So if the vector is v1 and v2 and length of the vector is square root of v1 square v2 square, if you divide v1 and v2 with the square root of v1 square v2 square, you will get a unit vector. Okay, unit vectors are very useful, especially when you are trying to find the distances between documents, okay, or many areas. One example is when you have in NLP, we will try to find distances between documents. You convert documents into vectors and then unitize them or normalize them, and then try to find the distance. It is going to be more appropriate. We'll see them in NLP, but here, for just to give an example, it is very useful. The normalization of vectors is a very useful concept. So I converted this v vector into this form, right? v1 by square root of v1 square v2 square and v2 by square root of v1 square v2 square. If you want to see whether this is true or not, this vector is unit vector, I am saying, this is true or not, we can do that. If you calculate length of this vector, how do you calculate length of this vector? This is the first value and this is the second value. Square root of first value square plus second value square. When you do that, right, denominator square root will go off and v1 square v2 square you will get on the numerator. The denominators are same, so you sum up and you get 1, square root of 1 and you get 1. Any vector you can make it as a unit vector by dividing it with the length of the vector, dividing the values in the vector with the length of the vector. So that is unit vector. Okay. So the next concept we are going to understand is projection of one vector on another. How to find the length of the projection of one vector on another. If you take two vectors u and v, I have taken a vector v and u. If v is being projected onto u, and if you want to find the length of the projection, you can use this formula. When you multiply the vectors, the product of vectors is equal to projection into the norm, the length of the bigger vector, the u vector, right? The projectile vector, okay? The projected vector and projectile vector, okay? So the u transpose v is the multiplication of two vectors is equal to p, the projection length, into norm of the vector, okay? So if you want to find the projection, right, projection is equal to u transpose v by square root of u1 square plus u2 square, the length of the vector u, okay? You unitized the u vector and then multiplying with the v vector, that's what is giving you the projection, okay? If the vectors are on the same direction, right, if both vectors are going in the same direction like this, then the projection is going to be positive. The vectors are in a different direction, this vector is going this way and this vector is going this way. If you have to project this vector onto this blue vector, you need to extend it and then project. So that's going to be negative. The projection value is going to be negative. So that's about the vector algebra, a little more vector algebra. These concepts are useful in many areas in machine learning and deep learning. Hope it's going to you get it and you remember it well. So we try to make things as simple as possible with simple examples. Thank you.